Hey, good afternoon, everyone. Welcome to this version of the GDP seminar. Today, we're happy to have Daniel Carranza from Johns Hopkins University, who's going to tell us about calculus of fractions for quasi-categories part two, continuing what Chris told us last week. Daniel, please.
Alrighty. Yeah, thank you for the introduction and for the chance to talk to you all. Yeah, I'm always very happy to talk to people about this project just because I like this project. So thank you all for listening. So I guess I'll recap kind of what we learned from last time. Hope to freshen up everyone's memory. So from last time, the goal is that we want to study localizations of infinity categories. And so as Chris said, these always exist, but in general, they're kind of unworkable and they have no nice properties. So we want some way of fixing that. And kind of the same problem shows up in one categories, and the solution that's it's in Gabriel-Zisman is the calculus of fractions. So if you have a pair that satisfies calculus of left fractions, then you can construct this this new category, which I'll call the category of left fractions, where the morphisms are much simpler, right? They're just spans where one thing is a weak equivalence. And the nice thing there is, oh dear, that's in blue. There's a second. So the nice thing is that if you have one category that satisfies calculus of left fractions, then so first of all, this kind of new construction that you come up with is the localization of C at W. But moreover, this category has some additional nice properties. So for instance, the Hom sets in the localization can be computed as a filtered colimit of Hom sets in C. And so this colimit will be indexed over some subcategory of the slice where you're considering things that are only weak equivalences. And it then follows from this that the localization functor will preserve any finite colimits that exist in C, and that if I started with a category that has all finite colimits, then the localization has all finite colimits. And I really mean all, not just the ones that come from the image of this functor, all finite colimits will exist. So then we kind of talked about what's our analog of the definition of calculus of left fractions for infinity categories, specifically quasi-categories. Okay, I'm missing more parentheses. So if you have a marked quasi-category now, then you say it satisfies calculus of left fractions, or CLF, if, first of all, W is closed under composition. And by closed under composition, so in quasi-categories, it's worth saying what this means, that if I have a composable pair of marked one simplices, then there exists some two simplex composing them, such that the composite is a weak equivalence, meaning it's marked, it's in W. And the second is that my pair CW as an object in the category of marked simplicial sets has the right lifting property against this, that was supposed to be a pointer, against this set of morphisms. So we kind of had drawings of what this looks like last time. So for instance, if I look, so I need these for all n greater than or equal to 2, and for all k not equal to 0. And for instance, if I look at n equal to 2 and k equal to 1, this lifting condition exactly corresponds to something like, given any span like this inside of C, where one morphism is marked, I can complete it to a full square, where, again, this corresponding morphism is marked. And In general, for higher n, this lifting condition will look like kind of completing a half cube, right? So this is a half square, completing a half cube into a full cube with weak equivalences kind of bouncing around depending on your definition of, depending on this parameter k. So this was our definition of the calculus of left fractions. And so now kind of that's, I hope, a fair summary of what Chris talked about. And so what we need to do next is we need to talk about what's our analog of the category of left fractions, right? So what's our version of an easier category that's gonna make the localization simpler to understand and work with. And so for that, we need an auxiliary construction. So for n greater than or equal to 0, I'm going to define a variant of kind of like barycentric subdivision that for simplicial sets. So I'm going to define a marked simplicial set, which I call SD plus. So I guess throughout this talk, a lower plus will denote like marked, which is maybe not the most standard notation, but is convenient notation for the purposes of this talk. I'm going to define SD plus. So just as in regular SD, this is going to be a, so the underlying simplicial set is going to be the same. Namely, it's going to be the poset of non-empty subsets of brackets n. Okay, not equal to empty. Sorry, maybe I should say this explicitly. So brackets n here is going to be our notation for this poset, the total linear order on integers from 0 to n. And but now I need to tell you what the marked one simplices are. So if I have a one simplex from A to B, meaning A is a subset of B, I'm going to declare that this is marked if the maximum of A, right? A is a subset of n. So if the max of A is equal to the max of B. Let's look at some examples. So for n equal to 0, my picture of SD plus of 0 doesn't change from the usual picture. It's just going to be a single 0 simplex because there's only one non-empty poset of bracket 0. For n equal to 1, I'm going to have a picture that looks like, right? So I'm going to start with the usual subdivided 1 simplex. And now I see that 0, 1, and 1 are subsets with the same maximum. And so this 1 simplex now gets marked. N equal to 2. Once again, I'm looking at the same subdivision of the 2 simplex, right? Zero, 1, 2. And now what are the 1 simplices that are getting marked? So 0, 1, and 1 have the same maximum. And all of these subsets that have 2 have the same maximum. And that's going to be all the marked 1 simplices.
Sorry, why are you not marking the rest? Don't they? What's the rule? Why is in the example n equals 1? Sorry, it's probably a very stupid question. But in the example n equals 1, why isn't 0 to 0, 1 marked?
Yeah, sorry. So the rule for the marking is a 1 simplex is marked if the 2 subsets that it's running between have the same maximum. So for 0, the maximum of this set is 0, and the maximum here is 1. So this would not be marked. But here the maximum is 1, the maximum is 1, and so this becomes marked.
Minus centralization. Thanks for it.
Sorry. Okay. Alrighty. Okay, so now we can define. Okay, maybe def define. It looks a bit funny. So now I'm going to define a functor called marked x, and this will go from marked simplicial sets to simplicial sets. And again, this should be very kind of reminiscent of the construction of cons or x functor, like for when you're doing Pfeiffer replacement in the Conquillan model structure. So Conquillan model structure. So this is just defined by palming out of marked SD. So on a marked simplicial set, say xw, the n simplices in x plus of xw will be marked maps from SD plus of n into xw. And I'll make a remark that if I start with just a simplicial set and I pass to marked simplicial sets via the maximal marking functor. So this is the functor that takes a simplicial set x and sends it to the simplicial set x x1. So by x1 I mean just it's disgusting. By x1 I just mean the set of all one simplices in x. So just mark everything. And then I use this marked x functor to go back to simplicial sets. Then this composite is exactly the original like cons x functor. Okay. And so the idea is that this marked x is going to be our candidate for the localization of C at W. And you can kind of see, right, that like, so if I started with a quasi-category C, then I apply x plus, the zero simplices would be maps out of the zero so the zero simplices would stay the same. The one simplices would look like kind of, right? They're marked SD shaped diagrams in C, right? So you're exactly seeing these left fractions, right? These spans where one thing is a weak equivalence, right? And your two simplices will just be these kind of marked subdivided diagrams. So this is already a much smaller model for the localization, if we can show that it's actually the localization. So the one thing we need before we can say that is an actual functor into the localization. So how do we get that functor? Well, we have a poset map, max, which goes from SD plus of n into n. And in fact, this map preserves the marked one simplicity, like as a map of simplicial sets, preserves the marked one simplices, essentially by definition of the markings in SD plus. And when I pre-compose, with this map max, what I get is a map which I'll call max upper star that goes from a quasi-category C to marked X of C at W. And you can check that this map, max upper star, indeed inverts the weak equivalences, inverts the marked one simplices in C. Maybe I'll just write this out for just so we can get a feel for like maybe kind of confirm what we're expecting for the X functor. So if I have a marked one simplex, say W from X to Y, then when I apply max upper star, the one simplex that I get as a result will just be the fraction where I put W on the left and I just put identity on Y. So you can check this is what happens when I send just the SD plus of 1 by max. So when I start with SD plus of 1 and I apply max, then this one simplex gets smushed. And then when I think of W as literally a map from a one simplex into my simplicial set C. And the inverse, so how you would conclude this proof is you would show that the inverse is given by just putting, sorry, the inverse should go from Y to X, right? So the inverse should be some fraction from Y to X, and it's going to come from just putting W on the other side. And since W is indeed marked, that's legal. Okay. So now I am ready to state the main theorem, maybe part 1, which is that if you have a marked quasi-category, CW, then firstly, so we actually have a kind of strengthening of the original result that that the category of left fractions is indeed a category. So we have that this pair, the pair CW satisfies calculus of left fractions. In fact, if and only if marked X on this pair CW is a quasi-category. I'll give myself more room here. And if this is, so in the case that CW satisfies calculus of left fractions, then we have that max upper star from this, our map from C to marked X of CW satisfy, or is the localization of C at W. Okay, now I want to talk about the proof of this theorem. So I'll start with the proof of, so, okay, the proof of part 1 is an if and only if. And so I won't like kind of walk through the details of how to prove it, but I just want to give a sense of like, what is it that we are like need to show when we unravel. So first I'll describe the reverse direction. So if you start by assuming that marked X is a quasi-category, how do you get that the pair CW satisfies calculus of left fractions? And there, the strategy, the thing that you need to do is you need to show that this inclusion of lnk into star of lnk is a retract of, in the arrow category of the map from SD plus of the horn into SD plus of the N simplex. So I haven't actually, I didn't say what like capital SD plus is, but again, this would exactly mirror the construction of like subdivision that you're familiar with from the Conquillan model structure. It's the extension by co-limits of the little SD plus that I defined for you earlier. And so X plus of CW being a quasi-category means that you have lifts against SD plus of inner horns. And since this is a retract, you have lifts against the LNKs. And so you have CLF. And now for this direction, which is maybe like the kind of intended use case of this theorem. Again, just kind of, I'm just going to give you a feel for what this requires, since in practice, this is a pretty, like, this is kind of a technical proof. But so you're trying to show that X plus of CW has lifts of inner horns. So say I give you like an inner horn. Let's picture a 2-1 horn here. Right, so this is what the maybe this is marked. So this would be, for instance, the data of a 2-1 horn in X plus of CW. And what you need to do is, sorry. So the idea is you look at the center of this horn, right? I'm going to see a span where one leg is a weak equivalence. And so I'm going to complete that to a square where this is a weak equivalence. Right, so given this inner horn, I fill to this new square at C bar, and then I compose. I'll put this in quotes. Right, the idea being that I have this one simplex and this one simplex. I just compose to get this fraction, and I would compose here to get this fraction. And now, so composition is kind of more like, that's kind of the easy way to say it in one categories. So in practice, like this requires like doing some kind of inner anodyne or some kind of anodyne like extension of this kind of diagram into the full N simplex. So this is where kind of the technical part of the proof goes, but this is the basic idea of what you need to do for step 1. Now let's talk about step 2. So step 2 essentially proceeds in part 2. Part 2 of the proof will proceed in 3 steps. So step 1 is to show that, right, so maybe let's, okay. Sorry, maybe let's remind ourselves of the goal here. So the goal is to show that max upper star is the localization. Okay, and now first we're going to consider the case when W here, the set of morphisms I'm inverting, is just already the equivalences. So I'm not really inverting anything at all. Right, so step 1 is if I have C going into X plus of C at marked at equivalences. Right. This is max upper star. Then a localization at nothing shouldn't change the category. So you want to show that this is an equivalence of categories. That's step 1. And it kind of, the proof of this is actually very similar to the proof like in the Conquillan model structure. There's this there's this neat proof in Latch, Thomas, and Wilson that like the natural map from X into, or from a simplicial set K into X of K is a Conquillan weak equivalence. And this proof, like with some minor modifications, essentially goes through to show this is a Joyal weak equivalence, which I think is pretty cool. And that's step one. Step two is we want to look at what happens when I apply X plus twice. So if I apply, so if I have X plus, and I'll give myself a little more room. So I start with X plus of CW, and then I apply X plus again of CW. And I need to pick some I need to pick some set of marked simplices. So I'm going to pick just the equivalences in X plus of CW. Now, there's two different maps that run between these two quasi-categories. The first is the kind of your good old-fashioned max upper star on X plus of CW, which by step one I know is a weak equivalence because I'm localizing at equivalences. But I also have I can also apply the functor X plus to the map max upper star of CW. And step two is to show that these two maps, that these two maps are E1 homotopic. Right. So by E1, I mean the kind of the contractible, the simplicial, the nerve of the contractible groupoid on two objects, right? So this would be the simplicial set that has two objects, 0, 1, 2, 1 simplices, F and G, and then two simplices, right? One that witnesses that FG is identity, one that witnesses that GF is identity. So this is, so I mean a homotopy out of this interval object, which is what we're thinking of as a natural isomorphism, I guess. Okay, that's step two. And I should say this is the most technical step. It's kind of the heart of the, maybe the technical heart of the proof. But now step three is the payoff. So, sorry. So first, by using this proposition that I talked about earlier, right? So the map max upper star from C to X plus of CW inverts W. So in particular, it induces a map which I'll call max upper star bar from the actual localization of C. Okay, so now I need to pull a diagram out of, now we need to draw the right diagram. So I'm going to take my map max bar upper star and put it up at the top of this diagram. Here's max bar upper star. Here I'm going to apply X plus to the actual localization of C. And I'm going to apply it at equivalences. And here I'm going to apply X plus twice to C. Okay, so now let's give myself even more room. Okay, so now I have the map. So I can apply X to max bar upper star. Down here, I have just max upper star applied to the localization. And along the vertical here, I have X plus of max. Maybe I'll move this to be below the arrow. And then the final map that I need is I'm going to need a map filling in this diagonal here. And this is just applying X plus to the localization map, which I'll call gamma. So gamma here is just the map from C to the localization of CFW, the true localization. So now this triangle is going to commute. It's a bit tough to see, but the idea is that you're to show that commutes, you're gonna use the universal property of the I should say commutes up to homotopy. This triangle commutes up to homotopy. You're going to use the way to show that is to use the universal property of the localization, and so that then you can consider like its homotopy commutativity when you precompose, and there it's just going to be a naturality square of gamma. Yeah, a bit again, that's a bit tough to see, but that's what it is. And this triangle so this triangle is X plus applied to like max upper star, gamma, and max bar upper star, right? And remember, max bar upper star by definition is the map which makes X upper star factor through the localization gamma. So that's why this bottom triangle commutes up to homotopy, because again, the universal property of the localization is up to homotopy. So the last thing we need is that, so this vertical map here is a weak equivalence by step 1, right? I'm localizing the localization, or I'm applying X plus to the localization with equivalences. This vertical map is a weak equivalence by step 2, because in step 2, we said that this map is homotopic to this map, and this first map is a categorical equivalence by step 1. And now we have 3 composable maps. The first 2 compose to an equivalence, the second 2 compose to an equivalence. And so I can apply the rare 2 out of 6 to conclude that every map in this diagram is an equivalence. So in particular, this map max upper star between the localization and X plus of CW is an equivalence. Yeah. I really like this proof because it's not often that you get to apply 2 out of 6. Yeah. I should say that I did not come up with this proof. This proof is from Zach. It's in his PhD thesis from a few years ago, and I mean, a lot of the stuff that's in this is based off of work in his PhD thesis. So huge credit to him for like so much of this, just about everything in this project. Yeah, I really like. Yeah, I think it's really cool, and I like sharing it with folks. So that concludes the main theorem part 1. And so already from this, we can look at a fun application.
Can I just make one comment before you proceed? It's a more question.
Yes.
Do you hear me? It's not quite a question, just a comment. When you started doing this, I was half expecting that you would start to do iterated access as Khan did for card fabric replacement, right? For card fabric replacement, you have to do infinity. But it's kind of neat that you don't, right?
Yes.
It's actually rather nice. But I guess on the other hand, you actually feed in more structure, right? Because you feed in a marked simplicial set, which is kind of more information than Khan was
Yeah.
allowing so, right?
Yeah.
That's maybe different.
So I guess there's sorry. So I guess there's maybe two things. There's maybe two ways to see to maybe two comments I can make about like iterating marked X. So the first comment is, as you said, like there's additional structure. Like, I mean, so the first part is that X plus is maybe I'll erase this. Sorry. So the first is just like a simple problem, right? That there's like a kind of typing error, but if you try and naively iterate marked X, right? Which is that these two don't have the same, like, this is not an endo functor, and so it doesn't make sense to iterate it. But of course, you can kind of impose, like, you know, you could look at specific one simplices in marked X and declare those to be marked. But maybe the more pertinent thing is that, and this is maybe some intuition, so nothing too rigorous here, which is that like kind of the way I think about fibrant replacement in the Conquillan model structure X infinity is that your one simplices will kind of look like zigzags. Sorry, maybe there's no markings here. Or alternatively, you're thinking of everything as being marked because you're trying to get a groupoid. And kind of the additional structure that you feed of calculus of left fractions is exactly telling you to cut down on this zigzag and just have like a span. So yeah. Thank you for your observation. I think it's a good one. Okay, so here's something kind of nifty. So there's a result in a paper of Meyer Azornova, which says that if you have a category C, then applying X to the and maybe a one category C, if you apply X to the nerve of C, then this simplicial set is Con if and only if the pair of C together with all morphisms of C, so I consider everything to be marked, if and only if this pair satisfies the classical calculus of left fractions. And it turns out that we can actually bump this theorem, we can bump this result up to a result for quasi-categories. That for any quasi-category, X of, and right, again, this is Con's X, X of C is a Con complex if and only if, when I consider the pair of C marked everywhere, this pair satisfies CLF. And this is a proof we can do right away. So X of C is a Con complex if and only if marked X of C at C marked at all one simplices is a Con complex, right? By this remark earlier that doing marked X at marked at everything recovers the original X functor. So now I claim that this happens if and only if X plus of C marked everywhere is a quasi-category, right? So why is that? Certainly if it's Con, then it's a quasi-category. But if it's a quasi-category, we know that if X of C is a quasi-category, then so if X of C is a quasi-category, then this is one of the equivalent conditions for saying that x of c computes the localization, right? So I'm localizing c at everything. So I get not only a quasi-category, I get a groupoid. And an infinity groupoid is exactly a complex, right? And we saw that this is equivalent to the pair C morphisms of C satisfying CLF. Yeah. So that's a fun proof that we can do right away. But maybe part two of the main theorem, right? We care about the co-limits, the localization having co-limits, and like mapping the Hom sets being filtered co-limits was a nice add-on for us. So here the theorem is if CW satisfies calculus of left fractions, and I additionally assume that W is closed under 2 out of 3. Then so first I have C, and the same formula. Okay, and the same formula works. So this is Y plus W, Y under W. Sorry. Right, so this is again some subcategory of the slice category. And so here, so I write it this way to kind of I have the sorry, that makes more sense. And then I have the mapping out of Homming out of C, the representable functor into spaces or infinity groupoids. Second of all, so using this, you can show that max upper star of the localization map preserves filtered colimits. Or sorry, finite colimits. And that if C has all finite colimits, then so does the localization. And so now maybe just to comment on something. So Chris mentioned earlier that in general, this colimit might be large. And kind of one upshot, so yeah, so Chris mentioned this, that so the only thing I wanted to add to this discussion is that here we have actually a precise thing that we have a precise condition we can point to in order to determine whether the localization of a locally small category is again locally small, which is that you need to show that this indexing category is finally small, meaning it has some subcategory and the inclusion such that the inclusion functor is a final functor. Okay, and I just want to give, yeah, okay, so I think I'm going a bit over time now, but what I want to give are some examples of when CLF is actually satisfied in practice. So the first condition is if I have some functor between quasi-categories, then if the source category C has all finite colimits and F preserves these colimits, like F preserves finite colimits, then when I invert C at F inverse of equivs, so by this I mean the set of one simplices which become equivalences under the functor F, when I invert at this pair, or sorry, this pair will satisfy calculus of left fractions. And the second example that's maybe worth saying is that if you have now an adjunction between quasi-categories, and I have a set of weak equivalences in the target of the left adjoint D. So D is marked at some set that satisfies CLF, and I know that so if D is marked at some set that satisfies CLF, and when I apply the left adjoint L to the unit natural transformation, so this should be a natural transformation, or maybe a delta one homotopy from L to LRL. But if this natural transformation is always marked, then the pair C together with L inverse of W, again, the set of one simplices which become marked under the left adjoint L, satisfies CLF. Maybe I'm missing squares on these. And I guess the point of this is that like this CLF condition isn't so rare out in nature. That like, I mean, these are often like, I mean, often you want to localize things which are the inverse of equivalences under some functor. And so this first theorem is very useful there because it requires, you know, it really doesn't require all that much. Right? It just requires that C has finite colimits and F preserves finite colimits. And the second theorem tells you that if I have some example that satisfies CLF, then I can pull back along a left adjoint to get another example of CLF. So yeah, I don't know. Should I stop here? Like I don't know how I'm doing for time. We have
more
time.
If you want to use it.
Thank you.
Excuse me. Do you have any specific? Do you have any specific example where you apply these theorems to obtain unexpected equivalencies satisfying the CLF condition?
So I can tell you two examples. I guess I don't know how, like, one is maybe more important to me than the other. I mean, both are important to me, but so one example that's easy to say right off the bat is in this second case. So in the second case, if I pick as W just the set of equivalences, and I know that my right adjoint is fully faithful, then like I'm actually, then D is a reflective subcategory of C. This condition will be satisfied automatically. And so what that tells you is that, so this is called a reflective localization, and that tells you that all reflective localizations satisfy CLF. So for instance, in higher topos theory, I think like all localizations are reflective localizations. But the second example, maybe that I know of, is which is kind of the motivation for at least Chris and I for embarking on the whole project, which is this example here. So here we use kind of the dual version of calculus of right fractions to essentially construct an infinity category for combinatorics. So in combinatorics, there is there's an area called discrete homotopy theory. And there you have like homotopical invariance of graphs. So you define things like homotopy groups and homology groups, but they're not the same as you would define them in spaces. They're defined so that like graphs can have arbitrarily non-trivial homotopy and homology groups. And so there's some, you can essentially construct some functor from so what happens there maybe is that you have a localization of graphs at what are called discrete homotopy equivalences. And this comes with some functor to spaces or infinity groupoids. But the problem is inverting at discrete homotopy equivalences doesn't actually work in this area. In this area, which you want to invert at a larger class of weak homotopy equivalences. And these localizations actually don't coincide for graphs like they would for spaces. And so, but you can use that this functor will preserve finite limits, and that this category has finite limits to construct a localization of the category of graphs, of some infinity. You can construct an infinity category of graphs, and this actually does compute the correct localization. And so you can kind of like study properties of this infinity category and like prove theorems in combinatorics, which is super cool. Thank you for the question. Okay. Sorry, so maybe I'll just, while we're on the topic of applications, right? So one that I mentioned, I guess I should have written this earlier, was combinatorics, specifically the area of discrete homotopy theory. But there's also the motivation. There's also an application to kind of string topology. I hope I'm using that term correctly. So this is there's a paper of Blumberg and Mendel from 2011, in which they use this. That uses this machinery, and
it's later. It's later.
Later than 2011.
Yeah.
Okay. Sorry.
The 2011 is way too early for this machinery. Yeah. Okay.
Sorry. Okay. Yes. Okay. Okay. Sorry about that. I guess I should check my sources a bit better. Okay, maybe two other. Sorry, I'll list two other applications, and then I'll conclude. So, two other kind of nice results that we have here is that if you have a pair that satisfies either calculus of left fractions or the dual version of calculus of right fractions, then W is saturated if and only if it is closed under 2 out of 6. So here saturated means that like a one simplex is marked. Saturation is the condition that a one simplex is marked if and only if it becomes an equivalence under the localization functor. So in general, yeah, okay, sorry. Lastly, I want to say that if you have, sorry, okay. If your pair CW satisfies both calculus of left fractions and calculus of right fractions, and blah. And you started with a category that was stable. You start with a stable infinity category, then the localization is also a stable infinity category. And so, okay, maybe I think I'll stop there actually.
Okay, great. Thank you.
We can talk more about this, like, but yeah.
Any further questions, Daniel?
Maybe I could just make a comment. Yeah, thanks. That was very nice and interesting. I liked, you know, what I liked best was the little lemma where you said that the marking is a CLF if and only if X plus is a quasi-category, right? So I think that actually,
Yes.
for me, sort of is the answer to why CLF is the right definition in the first place. That's pretty good, I think. That's nice.
Mm-hmm. Yes. Yes.
Because right a priori it looks a bit, it may look a bit contrived. Like, okay, somebody came up with this because it was clever, but now this seems to show why it's actually exactly the right condition.
Mm-hmm.
I mean, if you believe in X, of course, yeah.
Very good. Any other question?
Or maybe,
Yeah.
do one more. Maybe I have a vague question. So there's also this machine now of infinity categorical model categories, or whatever it's called, model infinity categories, right? By Aaron, Mays-Legree, and Hugh. So I don't know. This is used also to localize. Can you say anything? I don't know. This is a vague question. Can you say anything? Like, I guess your focus would be more general.
Yeah, so I guess unfortunately I don't know. I'm not very familiar with the model infinity category machinery. Yeah, if I were to guess, I would say they're kind of there may be like different solutions to the problem of localization in the same vein, kind of that like what the classical CLF is kind of a different beast than like the model category. It's a different answer to localization as opposed than like ordinary model categories as an answer to localization. That's just a total guess though.
So just going by another, like Szynski has vibration infinity categories, right? And vibration infinity categories don't satisfy CRF. They satisfy, again, a homotopy CRF, where the homotopy is now not the natural homotopy of your infinity category, but it's the homotopy induced by the weak equivalences of the vibration category. So whatever mismatch you had in the one categorical case kind of reappears in the infinity categorical case. So these are distinct solutions to perhaps the same problem.
Okay.
Any other questions or comments? If not, let's thank Daniel again for the very nice thoughts. Thank you. Thank you both, you and Chris, for the nice series.